Hello everyone, in this presentation we are going to look at some more operating system services. We are discussing about real-time operating system. Real-time operating systems are most widely used in the microcontroller based applications to make the application more robust if it is complex applications. So there are a lot of operating system services which is being discussed. The first one we talked about the shared data problem, and semaphore is one of the operating system services which helps in preventing the shared data problem. Similarly, there is something like inter-task communication. There is something like on-board communication, off-board communication. Similar to that, there is an inter-task communication where the task communicates among themselves. So as we discussed already, one task which is read temperature task is communicating with compare temperature task. So the temperatures are the values or the global variables which are shared between the read temperature task and the compare temperature tasks, where there is a possibility of shared data problem. So semaphores are used to prevent the shared data problem, like that we have discussed. So there is something like inter-task communication. So what do you mean by inter-task communication? Tasks can communicate among themselves is inter-task communications. One task can talk to another task. While the inter-task communication, there is a possibilities of shared data problem if there is a highest priority task interrupts the lowest priority task in the critical section. That we need to understand. In the round robin architecture, there is no possibilities of shared data problem, but in the round robin with interrupt architecture, are the tasks with highest priority and interrupt lowest priority tasks, there is a possibilities of shared data problem, but task needs to communicate among themselves. So there are some other real-time operating system features called as message queues, mailbox and pipes. These message queues, mailbox and pipes are very much used by the design engineers wherever necessary to exchange the data between the one task and another task. Okay, so let's take for example which is discussed in the chapter 7.1, and then we look at it. So there are two tasks. Let us say task 1 which has something to do, and task 1, if it finds an error, it has to report to the network. Similarly, there is another highest priority task, task 2, which finds an error which has to report to the network. So both the task 1 and task 2 have a lot more things to do, and reporting to the network is a time consuming task. So instead of waiting for the network, instead of task 1 waiting for the network, instead of task 2 waiting for the network, it is better to have another task which is error reporting task, which can collect the errors from the task 1 and task 2, and then whenever the network is available, that error reporting task can report that error to the network. So that error reporting task will be using one of the operating system services which is called as message queues, say for example. Okay, so because there is an error reporting task, task 1 need not wait for the interrupt, task 2 need not wait for the interrupt. Both the task 1 and task 2, when it identifies an error, it can send that error to the error reporting task through some function, log error function. So that log error function will add the errors into the message queues, and error reporting task will read the error from the queue, and then it will pass on to the network. So that is the best feature of this message queues. Okay, so several tasks are running with several different priorities, and several tasks has its own particular function. The task need not wait for the next task. Whenever the task need to communicate with another task, the data which need to be communicated can be given to some other common task. That task can pass on to the network. Something like we are having so many jobs, and we have to post the letter, and all of us, the 10 of us are there, means 10 of us need not wait for the postman to come. All the 10 of us can put our letter in the post box, where the postman will come and collect it at the particular time at 11 o'clock, means 11 o'clock. So the post box is something like message queues. Whenever we need to put a letter, we have to go put it in the post box. The postman will come and collect the letters, means the postman is something like error reporting task kind of things. So one way we can say that if there is no post box, all the 10 people have to wait for the postman by stopping their works. If there is a post box, they will come and put the letter and then they can continue their job. So one very important thing is post box is memory. So when there is a memory, we can keep the data into the memory and then we can go. If there are several tasks, the task need not wait for the another task to give the data. It can keep it in that memory and then it can go. And the tasks which are in need of that particular data, it can take from that memory whenever necessary. So the presence of memory will not delay the multiple tasks from its own speed. That is the one we need to understand. So let us say the port in a microcontroller, whenever the processor is running, the parallel port 0, port 1, port 2, port 3 is a good example, right? So port 0 is one particular latch, port 1 is one particular latch which is 90th location, port 2 is a latch, port 3 is a latch, 80, 90, A0, B0 and 80, 51, where an ALU, once the micro instruction like MOV P0, A means the current of the accumulator will be stored in the port 0 for within 1 microsecond. So because it is a memory, because port 0 is a memory which is a special function register memory, it holds the data of the accumulator and that data is sent out to the LED, means LED will be continuously glowing. But the accumulator current is given to the port only for 1 microsecond. The next microsecond accumulator will be reloaded with some other value for some other arithmetic operations or logical operations. Because of the presence of the memory, the peripheral device can take the data from the port whenever its own speed. So processor which runs with high speed, some other device which runs with some other speed. So both the device can run on their own speed without any disturbance, means in between there is a need for memory. If there is a memory, the high speed task can keep the content into the memory, it can go ahead. Low speed task can slowly come and take the content from that memory and then it can go. So memory is the only possibility where the high speed task can keep the data wherever necessary, whenever necessary. Low speed task can take the data wherever necessary and whenever necessary, where both the tasks, high speed task and low speed task, will not get disturbed. So this particular memory is called as message queues, mailbox and pipes, which in the application layer level, in the OS level, which we will be discussing very clearly. As told, there is a task 1 which reports the error to the network and there is a task 2 which reports the error to the network. So task 1, task 2 need not wait for the network. It can log error to the error reporting task. The error reporting task take the responsibility of sending that error to the network. Okay. For this kind of application, the service, one of the operating system service, message queues can be used. That was the statement of the author which is being mentioned here. So that is what being mentioned here, right? Suppose that we have two tasks, task 1 and task 2, each of which has number of highest priority urgent things to do. Suppose also that from time to time these two tasks discover an error conditions that must be reported on a network, which is a time consuming process. In order not to delay task 1 and task 2, it makes sense to have a separate task, error task, that is responsible for reporting error conditions on the network. Whenever task 1 or task 2 discovers an error, it reports that error to the error task and then goes on about its own business. The error reporting process undertaken by the error task does not delay the other tasks. Okay. So to do this particular application, RTOS queue is the way to implement this design. Figure 7.1 shows how it is done. So figure 7.1, when task 1 and task 2 needs to log errors, it calls the log error function. The log error function puts the error into the queue of errors for error star to deal with. Okay. So look at the figure 7.1, simple usage of the message queues. So there are two RTOS functions which are being used. One is add to queue function and another is read to queue functions. These two are the RTOS functions, and as told, there is a task 1 which is executing so many things, and if it identifies an error, it puts that error into the log error function. And there is a task 2, when it identifies an error, it puts that error into the vlog error. So log error is the function where task 1 errors are labeled as error type X and task 2 errors are labeled as error type Y. So whenever the task 1 identifies an error, it logs that error with the label error type X. Whenever task 2 identifies an error, it logs the error with the label error type Y. and it can continue its own speed. So this error type X and error type Y will be added to the add to queue function in the log error function. So add to queue function is a real-time operating system function where the error type X and error type Y's are added into the queue. Okay, so this is log error function, and there is something like errors task which takes the data and put it in the network. For that, error task uses read from queue real-time operating system functions. That is very important. Okay, so log error function uses add to queue real-time operating system feature to add or log errors into the queue, and errors task uses the read from queue real-time operating system functions to read the data from the error from the particular add to queue function, and then it can report into the network. So this is the one simple syntax where how the add to queue function and the read from queue function of an RTOS helps in logging the error into the log error function and reading the error from the error task function, something like that. So add to queue and read from queue are the two real-time operating system functions which are helpful for us to exchange the errors from the task 1 and task 2 to the network as discussed. Okay, so that is being discussed here clearly in this thing. So the add to queue function adds the value of the integer parameter. It is passed to a queue of integer values on the RTOS maintains internally. The read from queue function reads the value at the head of the queue and returns it to the caller. If the queue is empty, read from queue function blocks the calling task. So the RTOS guarantees that both of these functions are reentrant. This is very important. So the RTOS guarantees that both of the functions are reentrant. What do you mean by reentrant function? The reentrant functions are the functions which cannot be disturbed even though the program switches between the tasks. So for example, in the RTOS switches from task 1 to task 2, when the task 1 is in the middle of add to queue function and task 2 subsequently calls add to queue, the RTOS ensures that this still works. So without any shared data problem, it will work. Okay, so that is called reentrant function. Similarly, each time errors task calls the read from queue function, it gets next error from the queue, even if the RTOS switches from error task to the task 1 and task 2 back again in the middle of the call. Okay, so because errors task as well as task 1 and task 2 all are sharing the add to queue and read from queue functions, and this is very important. Even though they are sharing, shared data problem will not occur. RTOS ensures that is add to queue function of RTOS function and read from queue of RTOS functions will ensure that shared data problem will never occur. So there are some difficulties with respect to message queues in the real-time operating system, which was given us some ugly details. And what are the complications by using message queues here is being discussed. So most RTOS require you to initialize your queue before you use them. So we have to initialize the queue before we use them by calling a function provided for this purpose. On some systems, it also up to you to allocate the memory that the RTOS will manage as a queue. As with semaphores, it makes most sense to initialize queues in some code that is guaranteed to run before any task try to use them. Okay, we have to initialize the queue before we use the queue. So in most RTOS allow us to have many queues as you want. You pass an additional parameter to every queue function, the identity of the queue to which you want to write to or from which you want to read. So temperature queue, pressure queue, humidity queue, like that. You have to create the queues, and you have to identify the queue with the identity name, like temperature queue, pressure queue, humidity queue, etc. Okay, so that is what mentioned here. So if your code tries to write a queue when the queue is full, the RTOS must either return an error to let you know that the write operation failed, or it must block the task until some other task reads data from the queue and thereby create some space. So your code must deal with whichever of these behavior your RTOS exhibits. So we have to consider this parameter also by using the RTOS. Many RTOS includes a function that will read from the queue if there is any data and will return an error code if not. This function is in addition to the one that will block your task if the queue is empty. So we have to be very careful in looking at the real-time operating system queue features which is offered by the particular RTOS. Then only we have to use that queue functions. That is what the statement from here. So the amount of data that the RTOS lets you to write to the queue in one call may not be exactly the amount that you want to write. Many RTOSs are inflexible about this. One common RTOS characteristic is to allow you to write onto a queue in one call number of bytes taken up by the white pointer. So these are all the limitations which they are calling it as some ugly details. So it is in the general what statement is being given is it is mandatory to look at the RTOS feature from the offered RTOS before using it. That is what is being mentioned, right? So figure 7.2 is the same program as figure 7.1 except with more realistic RTOS function calls used in the micro C or OS. Okay, so 7.2 is the same program as in figure 7.1. So let us look at the 7.2. It is a new cause RTOS, the original RTOS. So here there is only opportunity for us to understand how the RTOS real-time operating system functions looks like. Here you see this is the RTOS queue function with respect to new cause real-time operating system. When it is a new cause RTOS, it starts with OS underscore. This is very important. New cause is an operating system which starts with the identity as OS underscore. So we are creating the queue. Okay, so we are creating the queue pointer, right? We are creating the queue with queue size. So this is the syntax for creating a queue in a new cause real-time operating system. This is the syntax for add to queue. So add to queue means queue post. Okay, so adding the content to the queue, the log error uses this queue post operating system queue post function or post feature of the new cause OS to add it to the queue, and read from queue is called as pend function. OS queue pend functions. Add to queue is post function, read from queue is pend function, which errors tasks are dealing with. So we have to create the queue and then we have to use the post function, we have to use the pend function for adding the error into the queue or as well as reading the error from the queue. So this is what the three RTOS features of new cause which is being used in this particular application, which is being clearly understood. Okay, so the event queue. Okay, so this queue, the size of the queue is being provided, and then we are starting our application code, right? Starting our application code. So here in this, the queue gets initialized before the tasks are started. So queue is initialized with the OS queue and the task was started. So first task 1, when identifies an error, it logs error with a label as error type X. Task 2 is running, it logs an error as error type Y, and the vlog error function uses the real-time operating system functions of add to queue, here more realistic, post queue post. So where the errors are added, the error reported by the task 1 and task 2 are added to the queue with respect to new cause RTOS syntax. And the error tasks which deals with the errors is using the read from queue. Read from queue syntax here it is pending, error type equal to OS queue pend. So P is OS queue, wait forever and byte error. So it is waiting forever and then the corresponding byte is being used here. This is the syntax, and this is the more realistic view of the application what we discussed in 7.1. This uses the new cause OS. When it is new cause OS means it is identified with the help of OS underscore syntax that is being discussed here. Okay, figure 7.2 is the same program as figure 7.1 except with more realistic RTOS function calls, the call used in new C bar OS. Okay, so the pointers in queue, that's what we have seen, right? All the add to queue or read from queue functions uses pointers. That is being mentioned here, right? Always RTOS uses pointers, right? Here you can see. So OS queue create is a pointer, pending queue is a pointer, and add to queue is a pointer, and so everything uses the pointer function. That is what message queues uses the pointer. So that's why pointers and queues. Figure 7.2 illustrates one fairly common RTOS interface and fairly one common RTOS interface which allows you to write one void pointer to the queue with each call. It is also listed the fairly common coding techniques people use to send a small amount of data, casting the data to this void pointer. The obvious idea behind this style of RTOS interface is that one task can pass any amount of data to another task by putting the data into the buffer and then writing the pointer to the buffer onto the queue. 7.3 illustrates this latter technique. Read temperature task calls the C library malloc function to allocate a new data buffer for each pair of temperatures and write a pointer to that buffer into the queue. Main task subsequently reads the pointer to the buffer from the queue, compares the temperature and frees the buffer. Okay, so read temperature task uses the queue functions which is being described in the chapter 7.3. So in the 7.3 the pointers are most clearly used here as told here, right? So passing pointers on queues. So queue function prototypes. Okay, so it uses OS underscore means because OS, and it uses pointers for adding temperature. It uses the malloc function, right? So memory allocation here. So after allocating 2 bytes of memory, the temperatures are added, and then it is posting, right? It is posting, it is reading the temperatures. So this is the read temperature task. Read temperature task uses the memory allocation function to read the temperature and put it into the memory allocation function as 2 bytes, and the main task, so which compares the temperatures, main task which compares the two temperatures by temperature 0 is not equal to temperature 1. So after comparing the temperatures, it frees the corresponding memory. So memory allocation on a malloc function while reading the temperature and freeing the memory after comparing the temperatures is one of the memory feature which is being utilized by the real-time operating system, which is passing pointers on queues. That is being told in the particular Simon author, which is called as pointers and queues. Okay, so the mailbox is something like SMS, as we type in an SMS, right? When we type in SMS, whenever the number of words are more than the predefined level, the message will go out as a 2 SMS. Okay, so when you are typing a big text message, your SMS will be transmitted as a 2 SMS. So that is something like mailbox. Your SMS can be considered as a mailbox. Okay, that is what. With that understanding, if you look at this mailbox, it will be very easy. In general, mailbox are much like queues. Typical RTOS has functions to create, to write to, or read from mailboxes, and perhaps functions to check. Whether the mailbox contains any messages, and to destroy the mailbox if it is no longer needed. Destroy the mailbox if it is no longer needed. Details of the mailbox, however, are different in different RTOSes. Some of the variations that you might see. So different mailboxes features are given here. So the first feature what we highlighted here is, although some RTOS allows us to certain number of messages on each mailbox, number that you can usually choose when you create a mailbox. Others allow only one message in a mailbox at a time. Once one message is written to the mailbox under these systems, the mailbox is full. No other messages can be written under the mailbox until the first one is read. One type of RTOS offers the mailbox feature like this. Another RTOS, the number of messages in each mailbox is unlimited. So there is a limit to the total number of messages that can be in all of the mailboxes in the system. But these messages will be distributed to the individual mailboxes as they are needed. This is some SMS kind of things. In some RTOSes, we can prioritize the mailbox messages. Higher priority messages will be read before the lowest priority messages, regardless of the order in which they are written into the mailbox. For example, there is a real-time operating system called multitask real-time operating system. Okay, so this multitask real-time operating system uses the mailbox as shown here. So there are 3 functions which are being used three real-time operating system functions which are used by this multitask RTOS. One is send message, another one is receive message, which is a pointer, and the check message, which is a pointer. So send message is the real-time operating system feature. Receive message is the real-time operating system feature from the multitask real-time operating system, and check message is the real-time operating system from the multitask feature. As we see here, you must create all of the mailboxes you need when you configure the system, after which you can use these three functions. Send message, so you can see send message, you are creating the message mailbox with the mailbox ID and the corresponding message pointer and with the corresponding priority. So we are sending the message with the priority, with the corresponding pointer, with the corresponding mail ID. So it is initialized. The mailbox is initialized in the multitask operating systems. Real-time operating system is like this. This is the syntax. And a device which need to receive this mailbox means this is the syntax. So receive message, unsigned integer message, mailbox ID, and it can wait for some time until timeout period. And check message means it can check whether the message from this corresponding mailbox ID. That's what the thing. So in all the three functions, the mailbox ID parameter identifies the mailbox on which to operate. The send message function adds the pointer into the queue of messages held by the mailbox ID mailbox with the priority indicated by the priority. It returns an error if the mailbox ID is invalid or too many messages are already pending in the mailbox. So the receive message function returns the highest priority message from the specified mailbox. It blocks the task that called if the mailbox is empty. Task can use the timeout function to limit how long it will wait for there if there is no messages. Okay. The check message function returns the first message in the mailbox. It returns null immediately if the mailbox is empty. So these are all the mailbox related things feature available in the real-time operating system. In this example, multitask real-time operating system, wherever necessary we can make use of this feature, mailbox feature, in a particular application if we are using RTOS. And finally the pipes. Pipes are also much like queues. Pipes are also much like queues. So the RTOS can create them, write to them, or read from them, and so on. Details of the pipes, however, like the details of the mailbox and queues, vary from RTOS to RTOS. Some variations you may see include the following. Okay, so these pipes are similar to message queues and mailbox with some small variations, as you see. Some RTOS allows you to write a message of varying lengths onto pipes, unlike mailbox and queues in which the message lengths are typically fixed. Where in mailboxes and queues, message lengths are typically fixed, but in pipes it can vary, message length can vary. That's one thing, right? Some RTOS allows you to write a message of varying lengths into pipes. Pipes in some RTOS are entirely byte oriented. If task A writes 11 bytes into the pipe, then task B writes 19 bytes into the pipe, then the task D reads 14 bytes from the pipe. It will get the 11 the task A wrote plus first 3 task B wrote, the other 16 that task B wrote remain in the pipe for whatever task reads from it. Okay, so task A writes 11 bytes into the pipe and task B writes 19 bytes into the pipe. So 11 plus 19, there are 30 bytes are there in the pipe, and task C reads 14 bytes from the pipe means 14 bytes from the pipe means it will get the 11 that the task A wrote plus first 3 the task B wrote, and then the other 16 the task B wrote remain in the pipe for whatever task reads from the next. Among 30, if 14 is read means 19 bytes. If among 30, that means task A writes 11 and task B writes 19. So among 30 out of 30, 14 is read means the remaining 60 will be there in the pipe. That's what it says. Some RTOS uses standard C library functions, fread and fwrite, to read from and write to the pipes. That's all. So what should I use? That's very important. Whether I should use the message queues, whether I should use the mailbox, or whether should I use the pipe that depends on the application. That's what it's given. Since queues, mailbox and pipes vary so much from one RTOS to the other, it is hard to give much universal guidance about which to use in any given situation. When RTOS vendors design these features, they must make the usual programming trade-offs among the flexibility, speed, memory space and length of the time that interrupts must be disabled within the RTOS functions and so on. Most RTOS vendors describe these characteristics in their documentation. Read it to determine which of the communication mechanisms best meets your requirements. So the author Simon itself is clearly mentioning that whether I should use the queues, message queues or mailbox or pipe depends on my application, depends on the RTOS, depends on the features of message queues, mailbox and pipes which each RTOS offers. Whenever it meets our application requirement, we can use that RTOS feature. It is up to us to choose. So this is what other real-time operating system features, which are message queues, mailbox and pipes, which we have to concentrate. So other things are pitfalls, which is not necessary. So when we work with RTOS, we have to look at those pitfalls and other things. For the time being, it is not necessary. The next topic we are going to discuss is timer functions. Now we'll stop with this here. Thank you.